Hello everyone, my name is Zhaoxin Chang. I'm going to introduce our recent work on behalf of all authors. The title of our paper is Unlocking the Beamforming Potential of LoRa for Long-Range Multi-Target Respiration Sensing. Wireless sensing has attracted significant amounts of attention in recent years, and various wireless signals have been explored for contactless sensing. While promising in many aspects, one key challenge of current wireless sensing technologies is to utilize the long-range multi-target sensing. This work explores exciting new opportunities to utilize long-range multi-target sensing with the introduction of LoRa. Based on the long-range communication capability of LoRa signal and the multi-antenna design on LoRa gateway, we explore how to use LoRa signals for beamforming to realize scanning of sensing targets in space. We take multi-target respiration monitoring as an example to explore how to achieve long-range multi-target sensing with LoRa beamforming. First, we introduce the LoRa beamforming primer. When there is a target at a certain direction in front of the transceiver, the signal on each antenna is a combination of a dynamic vector and a static vector. And the phase difference of the dynamic vector in any two adjacent antenna signals is the same. Therefore, if the signals of all antennas are aligned with this phase difference, that is, we rotate all dynamic vectors to one direction. Then, by adding up the signals on each antenna, we can enhance the dynamic vector, which is the energy of the target signal. On the other hand, the superposition of the static vector after rotation can be regarded as random. In this way, a signal with enhanced dynamic vector is constructed, which means this signal is focusing on the target. However, since the transmitter and the receiver of LoRa signal are not synchronized, the idle signal is multiplied by a term with a random phase. Thus, the phase of the beamforming signal is unusable for sensing. To solve this problem, we first construct a beamforming signal, which only has static component and has the same random phase item with the beamforming signal. Then we perform division operation on the beamforming signal and the beamforming signal. Since these two signals have the same random phase item, this item can be eliminated from the beamforming signal. And now, the idle beamforming signal is recovered and can be used for sensing. Another challenge is the traditional respiration sensing methods are based on the amplitude and the phase of signal. These methods are location dependent. Thus, in multi-target scenario, there is a high chance that some of the targets experience poor performance and even are undetected. To solve this challenge, instead of using amplitude and phase, we find that the curvature of the signal in a complex plane is a location-independent feature for respiration sensing. We calculate the curvature of the signal to find the changing points of the respiration. We can observe that for different targets, although the amplitude and the phase of signal have different scales, their curvature scales are the same. So this is a location-independent signal feature for respiration sensing. Here is a demo of our system. There are 3 targets in the environment, and our system can monitor their respiration rate and waveform at the same time. This is a through-wall scenario, and 3 people are sitting side by side. This is a long-range scenario, and the distance between the targets and the transceiver is 15 meters. Thanks for your attention.